Alright, so we are recording now, and let's go to the practice quiz, the very first problem. Let me have you start with that one. Alright, and anybody still need more time on problem number one? Alright, let's go ahead and look at it. The derivative is, it's the chain rule, and I mean it's the quotient rule. So it is the bottom times the derivative of the top. Now when I take the derivative of ax plus b, I got to treat a and b as constants. Minus the top times the derivative of the bottom and that has a number of constants over the bottom squared and then this derivative with respect to x is just a, because that's a constant like 5x plus 2. The 2 would go away and the 5 would be all that remains. And this derivative is 2cx plus d, and that's it. So then I'm going to get equals, let's get a little more space here. This a, I'm going to distribute to everything in here. I'll keep them in alphabetical order. And then this and this are going to FOIL out. Minus, and if I distribute the ax, I'll get everything will be positive inside this bracket. Plus, oops, tried to scoot over a bit, and what did I do? Oh, I just went to a whole new page. Alright, plus, let me just go down here. 2bcx plus bd. And all this is over And then I would distribute this minus sign, make all four terms negative, and any like terms, the ADX's are going to cancel out. So those two will cancel, and I will wind up with equals. Now here's 2acx squared, and here is 1acx squared. So when we combine a negative 2 and a positive 1, we'll get a negative 1 of those. So these two like terms combined. And then minus 2bcx minus bd all over cx squared plus dx plus e squared. And that's it. And if y'all can give me some feedback on that, go into the main channel. How are you with problem 1? Everybody give me just a little bit of feedback. Okay, the constants being letters, that's a thing that we can maybe reinforce a little bit more. Okay. Alright, let's go to number 2. This says 1 again, but this is number 2. Okay, I'm going to give just 30 seconds more, and if you don't get all the way through it, it's okay. You can just check with what you got so far. So this one, we need two rules. We need a product rule to do the numerator. We need the quotient rule to do the numerator divided by the denominator. But we need the quotient rule first, because that's the only way we can look at the whole problem all at once. So I'm going to use the quotient rule first, and it's the bottom times the derivative of the top. Minus the top times the derivative of the bottom. All over the bottom squared. And when I work this out, I get, alright, so inside this part, I'm going to put these two together, and that'll be the first, and that'll be the second. A constant can go with either one. So this is going to be unchanged. The derivative of this, I need the product rule first times the derivative of the second. When I take the derivative of e to the 2x, I get e to the 2x again. E to any power is just that. But you also get a 2. Showing up there. So the derivative of e to the kx, we had stated as a rule, was k times e to the kx. And then plus the second times the derivative of the first. And that's going to be 6x. And so that's expanding out what was in this derivative. Minus 3x squared e to the 2x. And then the derivative of the 1 just goes away. The derivative of secant is secant tangent. And if you don't have all the trig functions derivatives memorized, you're going to need to do so really quickly. Alright, so then we're going to clean this up a little bit. F prime x. This first term up here in this second parenthesis could become 6x squared e to the 2x. That gets multiplied by the x, the secant of x. So that's going to be 6x squared e to the 2x secant x. And then the secant x also distributes to this next term. Plus 6x e to the 2x.
Freaking out. I can't be with him every second. Like, why? Just all of a sudden I have to like be on with him. I have a few other things to take care of. You asked for too much.
You can mute your mic. And then we distribute the 1. So then it's plus 6x squared e to the 2x. Distribute the 1 again. Plus 6x e to the 2x. And then this last term is minus 3x squared 2x secant x tangent x. All this is going to get divided by secant x plus 1 squared. And then I look to see if there's any like terms in the numerator. There's a minus 3x squared e to the 2x secant x tangent x. That's got a tangent x, this first one doesn't, so it's not. These are not like terms. That's got an x, so that has an x squared. They're not like terms. I don't see these two right here. So no, that one's got an x. That one's got an x squared. So none of those are like terms. So that's the final form.
Mr. Shankin,
Yes.
can you explain to me why the derivative of e to the 2x is 2e to the 2x?
You bet. All right. The derivative of e to the x is e to the x. The derivative of e to the something like 2x is, we're going to actually finally get an explanation for this after today's lesson. We'll come back to this problem after today's lessons. But for right now, the only way that we know that is I had given you this rule. When there's a constant in front of the x, that constant shows up again. In front of the derivative. And so that was just a rule to be memorized. After today, though, we'll be able to explain why that's true. All right. Sorry I can't give you a better explanation for that now, Bianca. But that's the best I can do at this point. Okay. Can you all give me feedback on this one? Let's go to the text channel. I know this is one of the lengthy ones, but that's the kind of stuff I need the feedback on. Okay, yeah, and I'm not giving you enough time really to fully work it out, but hopefully you're getting enough time to see, oh, this is where I'm making a mistake, or this is where I get stuck, or something like this. Okay, trig functions in general might need more work. Okay. All right, let's go to number 3. There's a drawing of f of x, and on the same grid, draw f prime of x. All right. Let me know if you need more time still. Don't hesitate to interrupt if you do. Just let me know. All right, so we're going to go here and here. Those become the x-intercepts. Because we're drawing pictures of the slope where the slope was 0 here and here. Now, in between these, the slopes are always negative. We're losing money in the stock market. And it's most steep right here. If you're skiing down this hill, you're going to be going the fastest, most terrified right about here. That's where you're going to be at your steepest point, like here. And then after this, you're getting more and more positive. Now, we don't know enough whether this should be a straight line or a curved line, but it should definitely be above the x-axis. This is always positive slopes. If you bought stock here, you'd be happy. Something like this. So, the particulars of this can vary quite a bit, but the intercept should be there, should be below it, in between. If you had a more like a V or instead of a U, that'd be okay. Let me know where you're at with this. Give me some feedback on number 3. Okay, there's a fair amount of people feeling pretty comfortable, and I think this was really tough at first, taking a while to get used to this. Different way of viewing math. Alright, let's go to questions on homework. So 3.6 was due, spot check was due today. 19, let's start at 19. Alright, so we need all the directions here. Alright, so it says suppose the position of an object moving horizontally is given by this, and then where S is measured in feet, S is 0, corresponds, S greater than 0 is to the right. Okay, graph the position function, finding graph the velocity function. Alright, so the position function for number 19 is this one that's right here. And oftentimes F is the same as S, as they were alluding it to, so we could replace this F of t with S of t. And then I noticed that there's a t common to everything. And 2t squared minus 21t plus 60. Alright, so when t is 0, this thing is going to be 0. And then this is a third degree polynomial for the original function, but if I needed to graph this, I'd want to find the x-intercepts here. The x, where this, or it's now the t-intercepts, where this is going to intercept the t-axis is going to be the solutions of this equation. Because on the t-axis, the height is 0. And so we use the quadratic formula. Negative b plus or minus the square root of b squared. Now 21 squared, it's always going to be positive. And then I would get my two answers, and I would get one of them, I'd put them both in decimal form. And does anybody have these two answers? If you solve this with the... Now, I could, in theory, perhaps factor this, but with numbers that big, I usually only factor if I can kind of see it really, really quickly. If it doesn't factor really quickly, I just jump right to the quadratic formula.
I got 2 and 5.
2
and 5.
and 5. Now, if they're the whole numbers like that, then this should have factored. That's a nice way to kind of check it. We would have had t minus 5 would have been one of them, and then 2t minus to get 2, it would have had to have been 4, so then that's... I'm not sure that I'm getting the same thing.
On a way I was shown, the 21T turned into a 42T, and I didn't understand that.
When we take its derivative, we'll get that. We'll get that in a little bit. Right now, we are just trying to find the x-intercepts of this. So let me punch it out in my calculator. I'm not sure I'm agreeing with 2 and 5.
2 and 5 are the intercepts of the derivative, not of the original function.
Not of the original. Oh, okay. Does anybody have the intercepts here of this original? We would need this to do part A, graph the position function. So it wants the intercepts. Okay? So let's go.
Can you take a 2 out of the whole function?
No, because the middle term is odd. Okay. So I don't want to take up too much time with this one because we kind of have a long section here. So this is just some computational details. If somebody gets this later, they can add this in and we can look at that. But for right now, let's go to, so that was part A. We're going to leave it kind of incomplete because we don't have these in decimal form. All right. Part B, find and graph the velocity function. So here is A, and we'll leave a little space. We can come back to this later. Maybe during the break I can come and do that. For part B, we're going to take the velocity, which is the derivative of the s function. And we just take this function right here, 2t cubed, and it becomes 6t squared when we take its derivative. Minus 21t squared becomes minus 42t. And I'm taking the derivative of that. Take the derivative of 60t is plus 60. Alright, so then we take this and it says find and graph the velocity function. When is the object stationary, moving to the right, moving to the left? Alright, so we're going to take this is my velocity function, and I can factor out a 6 right away. T squared minus 7t plus 10. Alright, now this factors the two numbers multiplied to be 10 have to both be negative. And then I can see that now here my t equals 2 and t equals 5 are when the velocity is 0, because we're going to get 0 for this equation. Velocity is 0, or object is stationary. Alright, and then we can graph this whole function. Now this is a parabola. Since a is positive, it's an upward parabola, and we know the two x-intercepts at 2 and 5, so this one I can graph. T and v of t, and it's going to be some upward parabola. Like this. Now, this is the derivative, because it's s prime. And when the derivatives are negative, we're below the x-axis, meaning that, so to answer this question, when is the object stationary? We did that at 2 and 5. When's it moving to the right? It's moving to the right when the velocities are positive. So, moving right when velocities are positive, which occurs when we're above the x-axis for the velocity, which is when t is less than 2 and when t is greater than 5. And moving left when the velocities are negative, and that would be 2 less than t is less than 5. When t is stuck between 2 and 5, that's when the velocities are negative, there and there. Determine the velocity and acceleration of the object at t equals 1. Alright, so for part C, we're going to need to find the acceleration. We already found the velocity. Acceleration is the second derivative. And so we take our answer for the first derivative, this one, and we take its derivative, and we get 12t minus 42, and that's it. And then we find a of 1 and v of 1 and so on. And let me see, determine the acceleration when the velocity is 0 on what intervals of speed increasing. All right, I would like to leave the rest of this to you guys, but I've got you going on it. And that's as much of 19 as I'd like to do, unless there's a really specific question. Does anybody like got stuck on a later part and just says, can you give me a help with a little something here? All right. If not, then yes.
I got stuck with number E.
Okay. On what intervals is the speed increasing? All right. Now, when the speed is increasing, that's going to be similar to all right. Speed is the absolute value of the velocity. When your speed is increasing, that's the same, roughly the same as when your acceleration is positive. So the basic idea is here is when the acceleration is greater than 0. Now, that can have an exception, but that's the basic idea of this, is on what intervals is the speed increasing. So you want to look at your acceleration function, and our acceleration function is this one, and then when is this going to be positive? When this is negative, like for instance, if t was 1, we'd get a negative acceleration. But if t was 10, I'd get 120 minus 42, which is positive. I'd get a positive acceleration. So you want to find all the t that would cause this to be a positive acceleration. Okay. Other question was 29. Let's look at that. Average marginal cost. So let's go to the snipping tool. All right, so find the average cost and the marginal cost. All right, so the marginal cost, this one, is C prime. So we just take this and we take its derivative. For the average cost, formula we gave, remember it was C bar of x, which is C of x over x. Okay. And then, all right, so let's go the marginal cost. We take its derivative and we get 0.1. The average cost is 1,000 plus 0.1x divided by x. Okay. And then That's the answer for part A. For part B, determine the average and marginal cost when executed.
Mr. Shankin?
Yes.
So in the textbook, it gives you for the average cost, it's 1,000 over x plus 0.1. Is that the same thing?
1,000. Hold it. They get 1,000 over x plus 0.1. How could they have gotten that?
I think they separated the numerator into two fractions.
Oh,
So
yes,
1,000 over
yes.
x
Okay.
plus 0.1 over x.
Okay, gotcha. That's the same thing. That is correct. So c bar of x, if you make it two fractions, it's 1,000 over x, which is the same as 1,000 x to the minus 1, plus 0.1 x over x, which is 0.1. Okay? So it could be written like that as well. Okay. And then part B is c prime of 2,000 is 0.1. And then interpret is part C. Interpret the values that you got in part B. The interpretation of this, the marginal cost is the cost of the next item. So this would be the cost of the 2,000th item is 0.1.
In the textbook, it says 2001.
The 2001st item?
Yeah.
Okay. It could be either one. It kind of depends on whether you place more emphasis on what's coming right after it or right before. But let's stick with the convention of the textbook. If that's what this textbook does, let's do the same thing. Cost of the 2001st item is 0.1. And then the average cost if you made 2,000 items. Now this is not just the 2,000th item. It's the average cost of all 2,000 items is 1,000 over 2,000 plus 0.1, which is 0.5 plus 0.1, which is 0.6. So this is the average cost of the first 2,000 items is 0.6. Maybe that was in dollars, or who knows. Didn't really tell us. All right. Does that make it clear on 29? Any further questions there?
So when we do, I'm guessing this is going to be on the test. When we ask, are you going to ask for what each like marginal cost means of A and the derivative cost, or the, what is it called? Average cost. And then what it means. So do you want us to emphasize on the before the 2,000 item is reached, or do you want us to do it like the textbook as the 2001st?
Either one technically is correct. So it's kind of like when we interpreted the derivative. It's like in 2016, the profit is going to increase by $45 million in the next year. And I said, it's not really fair to favor the next year We could have said the previous year as well, because either one we're staying on the tangent line. But very often we are using it to project out into the future. So, but it actually could have gone to either one. So either one would be correct on the test. And the tricky part about this, I think, is the interpretation. And to say that, the derivative, what it essentially means is that the change in the output when the input goes up by 1. So C prime is going to be the inputs go up by 1 means one more item is made. And then the change in the output is C, not the C prime. So the cost will go up by 0.1 when one more unit is made. So it's the cost of that very next item. Okay, and all right. Let's look at the last one, number 36. All right, feather is dropped on the moon. On the moon, a feather will fall to the ground at the same rate as a heavy stone. Did you hear about the restaurant on the moon? They say it has great food but no atmosphere. Suppose a feather is dropped from a height of 40 meters above the surface of the moon. Then its height s in meters above the ground after t seconds is s equals 40 minus 0.8 t squared. Determine the velocity and acceleration of the feather the moment it strikes the surface of the moon. Alright, so if I was to draw a picture here, it would be 40 meters high that we're here's my feather, and here's the surface. And from here to here, it's 40 meters. And its height s is 40 minus 0.8 t squared. All right, and notice if I made a little table of values. If I put 0 in here, I'm going to get 40, meaning I start out at the height of 40 meters. And as t goes up, this number comes down. It's 39.2. As t gets higher and higher, this number gets lower and lower. Eventually, it's going to come down to s equals 0. At the point when it's s equals 0, the equation doesn't apply anymore. The feather has hit the surface. So it just applies till that point. And we're going to determine the velocity. That's the derivative. And acceleration. Alright, and this number right here, 1.6, if this was on the surface of the Earth, it would be 9.8. That's how much smaller the acceleration is on the surface of the moon than on Earth. And now we need to fill in these at the specific time when the feather strikes the surface of the moon. How do I find, though, when does it strike surface? Anybody have an idea? How do you find out? Eventually this is going to
Can't
lead
you
to...
find when t? Can't you find t? When s equals 0,
That is
just set
correct.
s to 0 and then solve for t.
That is correct. We're trying to find out this value when s is 0, so we're going to put the 0 in right here. Leave the t as t. And then solve this thing for t. You're going to get two answers. If you get a negative answer, it wouldn't apply. A positive answer would apply. And then you can come back and substitute it into either one of these. All right, so that's as far as I'm going to take this one. I think you can take it from there yourselves. And are there any other general questions before we move on? Yeah, kind of a dad joke. Yeah. Yeah, a dad with at one time very young kids. That was one my kids liked. All right, let's go to 3.7, the chain rule. And this is an extremely important section. All right. And we're going to switch over to, I'm going to use my whiteboard and clear some space here. Let's go to the camera. All right. What we can differentiate. By differentiate, I mean what we can take its derivative. What we can differentiate now. We can differentiate any function f as long as the function is kind of like a polynomial, like x to a power, and then or if it's an exponential function, or if it's a trig function. So we have quite a few functions that we can differentiate. Plus, we can say, if I add two functions, I can still take the derivative, because I have a rule for that. And if I subtract two functions, each of them I could take its derivative, I could take the derivative of that. If I multiply two functions, now it becomes more difficult. When you take the derivative of the product of two functions, you have to use the product rule. But you can still do this. And if I have the quotient of two functions, each of them that I could take the derivative, I could take the derivative of this. And that gets even more complicated. It's the quotient rule. And I could also take the derivative of a constant times a function. So this is basically all the different kind of things that we can take the derivative of now. And let's say let f of x equal x to the 10th and g of x equal the cosine of x. Now, if that was the case, I could take the derivative of these two added together, because I just take the derivative of that plus the derivative of that. It would be 10x to the 9th minus the sine of x. And I could do every single one of these, combining these two together. But there's one way that I could combine these two together that I would not now know how to take its derivative. Can anybody think of the way that these two could be combined together that we would have a problem taking its derivative? Anybody?
As a composite function?
That's right. Let's look at that. If I put one within the other, so what we can't do yet is if I have something like this or this. And these are called composite when you place one function within the other. Now, if we place one function within the other in this manner, what would I wind up getting? F of g of x would be, and let me give you a minute, see if you can write out what this function would be, and see if you can write out what this function would be if you place the one inside the other. They'll both have cosine in it and they'll both have 10 power in it, but they'll be looking different. So I'm going to give you just a minute. And if you're not sure, just take a wild guess. You can see if you're right in a moment. All right, for this one, so what this is really saying is f of anything is that thing to the 10th power. And g of anything, well, let me write it underneath there. G of anything is the cosine of that thing. So if I did f of g of x, it would really replace the g of x with cosine x. And then substitute cosine x in here. So it's cosine of x to the 10th power. And we have a shortcut way of writing that like this. So that's what this one would look like. If I put the f of x inside the g of x, you just replace the inner one with what its real value is. G of anything is cosine of that thing. And notice how these look different. They're actually quite different. But when you place one function within another function, and then you ask, what is the derivative? So we would be asking, what's the derivative of this, or what's the derivative of this? That's the topic for today. How you take the derivative of what we call nested functions, when one function is inside the other. So let's take f y equals, suppose it was this second one, cosine of x to the 10th power. Then dy dx equals what? That's today's topic. And we'll get into this. It's extremely important. It opens up this huge world for us because we find that functions within functions are perhaps the majority of the functions that occur in the real world. When we really model real things, they're usually not simple. And so we really need this. So it is time for a break. We will start again at 12. If I had 15 minutes, it's 12:48. I'll see you in 15.
Professor, are you recording?
Yes, I am recording. Thank you for checking. I set that up right at the beginning today. All right, let's start up again. And during the break, I went back to problem number 19 that we had looked at earlier. It's giving me a little bit of problem. All right. So on the original function, we had factored out a t, and then we got this quadratic left over. And if you set that equal to 0, you'll find all the places where this function intersects the t-axis. And when we plug it in, and then when we punch it out in the calculator, this turns out to be a negative number. And what does that mean? That means that there's no solution to this portion, which means that there's no more no more t-intercepts. T equals 0 is the only legitimate t-intercept. And so now when I went to Wolfram alpha and I plugged in that function and it graphed it, and notice t equals 0 is the only place it hits the x-axis. If this would have kind of come down and intersected the x-axis, then we'd have had two more solutions. But where it came up with a negative number inside the square root, meaning no solutions. And so now we can see that how this correlates. See, right at 2, the velocity was 0. The derivative is 0, horizontal tangent line. And to the left of 2, it's a positive slope, meaning we're increasing in velocity. And then it's kind of like we're going away from home, going back towards home, and then away from home again. Increasing velocity, decreasing, increasing, and that all is consistent with the picture that we had drawn over here, which, let me come back one more time. Picture here that the velocity's positive, negative, positive, and velocities positive, negative, positive. All right, let's continue on. Does that add a little bit more insight? Any other questions relating to number 19? All right, let's continue on. And all right. So when we're trying to take the derivative of a function within another function, what we're going to need is the chain rule. And I'm going to start with this example. F of x is equal to 2x plus 3 to the 8th power. Now, I'm going to look at this function as really two functions. There's an inner function and an outer function. What's the inner function? And what's the outer function on this one right here? And 2x plus 3 is on the inside. So I can think of that function coming here. 2x plus 3 to the 8th might be my hunch for the outer function, but when we simplify that, we just think of it as x to the 8th. If we think of it like this, then suppose j and k were these two functions. Then f of x will be, now how would I put j and k together? Would it be j of k of x? Or would f of x be k of j of x? Which one of these will recover this right up here? So I'm going to give you a moment to go into your groups and see if you can become real clear which of these two would be correct and why, and I'll get with you in just a minute. So. Anybody need more time? All right, let me ask group 4. Which would it be and why?
It's the second one because the function k is the outer one, and that goes with the second one, and j of x is the inside function.
So this one is not true, and if we just replace the inner one, 2x plus 3, k of anything is that thing to the 8th power, and we get this, which then agrees with the original. Okay, so this skill of being able to differentiate what's the inner function, what's the outer function, is going to be really important to us to be able to execute this chain rule. So I'm going to list some functions, and on this one it's pretty clear. I mean, that's the inner one, that's the outer one. But some of the other ones, it gets a little bit kind of tricky. So we'll call that problem 1. Let's go to number 2. F of x is equal to e to the 3x plus 4. Let's make an inner function j of x, an outer function k of x, and you pick which is which, and go ahead and work in your groups, and I'll pick on a group in a moment. All right, group 6. Any ideas?
Possibly j of x is equal to e to the x, and then k of x would be equal to 3x plus 4.
Let's check it out. If that's the case, then we are going to be, the inner one would be j, the outer one would be k, and this would be e to the x, replace the inner one with it, and then k of anything is 3 times that thing plus 4. Now this isn't matching up with this. Alright, so it's very instructive. If we get them backwards, we can just verify by just placing the inner one inside here and then working it out. And let's flip it around and see what happens if that takes place. So the 3x plus 4 is going to go over here, and the e to the x will go here. And notice the simplification that was made. It's not e to the 3x plus 4, it's just you make it e to the x. And then if we do this one, the inner function is 3x plus 4. This k is e to e to a power, so e to the 3x plus 4. And now this one will match over here. All right, so now the easier way to determine, the easiest way that I think of to determine the inner function and the outer function is, suppose x was a specific number. Suppose x is 2. What's the first thing you have to do to 2? You have to multiply it by 3, and then you have to add 4 to it. So the inner function has to be the first things that would happen to that x if you were evaluating it at a specific value. So that's why the 3x plus 4 has got to go on the inner function, and then the last thing that would be done is raise e to whatever that power turned out to be. Okay. And let me do another one. And this one is going to be really tricky, but I'm going to change the question. It's cosine cubed 7x plus 5. And the question now is not what's the inner minima, it's what is the outermost function. All right, consult in your groups. What is the outermost function for this one? Call on one of you to know. And let's just say that in general now, one of the first things you do when you get online today is make sure that you know who's the spokesman for your group, or you can do that as the last thing each day for the, before you take off for the next day. Is people figure out who's going to be the spokesman for the coming day. All right, group 2, what's the outermost function?
We have that the cosine of x, it looks like you would plug your x first into the inner function, and then it looks like something's being cubed, and then you would take the cosine of it.
You're really close.
The cube.
Quite. This one is deceptive in its format. What this really means really has 2 L's. Really means is this. Cosine of 7x plus 5 that is raised to the 3rd power. And this is shortcut notation for this right over here. And notice that it does save quite a bit of time. Instead of having to put this extra bracket here in this cube, it's really compact notation. But when it's seen this way, we can see the innermost function is 7x plus 5. The next innermost is cosine x. And then the outermost function is x to the third. So what's the outermost function? It's just cubing. Right here. And the ability to identify the outermost function will be actually more important than identifying inner and outer. We'll always be working and coming to the conclusion, what's the outermost function each time, and we'll use that as we take the derivatives. All right. Any questions here? Is this clear so far? Okay. And group 2, that was Jay, you're in that group as well. Hopefully, I told you the group number. I was telling you where you're at.
Yeah, I got where I am.
Okay, good. And all right, let's go now to this first function, this first example, the chain rule. All right, we're going to find the derivative f prime of x via the chain rule, and we're gonna do it where I'm going to just show you how to execute the chain rule first. And once you get good at executing the chain rule today, then I'll go and I'll describe why the chain rule works the way it works. But first, we'll just get comfortable with the procedure. And the procedure for something like this is, well, there's really a constant out in front, 1. And just like we would take, if I had y equals x to the 8th, we'd take its derivative by saying y prime is 8 times 1, 8x to the 7th. We're going to do something very similar here when we have a function within a function. We're going to take the 8 times the 1, and we're going to get 8. We're going to get 2x plus 3 to the 7th. So notice I'm working with the outermost function, which is something to the 8th power. And I'm taking the derivative of that as if this something was just an x, but it really is more complicated. It's 2x plus 3. Then I have to chain on the derivative of the rest. In this case, it's just that innermost function, 2x plus 3. And then f prime of x, this derivative is 2. So 8 times 2 is 16, 2x plus 3 to the 7th. So the chain rule is we're going to, the way we're going to execute it is we're going to take these things, multiply them, and we're going to do it like this. What was in parentheses, the inner function was just an x. But then we have to take its derivative at the end, like this. All right. So let me have you do number 2. If y is equal to 5x minus 7 to the 4th power, you find dy dx. Let me give everybody a minute. All right, so 4 times 1 is 4. 5x minus 7 to the third. Chain on at the end the derivative of everything but the outermost function. We took the derivative of the outermost, everything else goes right here. Then we take its derivative, and that's 5. And then dy dx. 5 times 4 is 20. 5x minus 7 to the third. Any questions? All right. We're just doing how to execute it without much of the theory at this point. But let's just get this down. Number 3. Let's take y equals the cosine of 8x plus 3. Find y prime. Now, this one certainly looks different than this one, but we approach it in a similar way. What is the outermost function of this one? Certainly it's not the 8x plus 3, so it's got to be the cosine. So if cosine is the outermost function, that's the thing I take the derivative of first, just like I took the derivative of, 4 something to the fourth. So I think of this as cosine of something. And then when I take the derivative, think of as cosine of something. When I take the derivative, I'm going to be getting the negative sign. This thing will still stay the same. And then I'm going to take the derivative of everything else except that outermost function. And when I take that derivative, this becomes 8. So I get y prime equals negative 8 sine x plus 3. Like that. All right, we're getting some extra noise. Let me take a look. Christian, I think your mic might be open. Okay. All right. Any
We
questions?
can't see the whiteboard.
Pardon? Oh, thank you.
I can't see.
Let me put it back to the whiteboard. And let me take a quick print screen. And let's come back to here. I think I did, that was 3, so let's do number 4. And this one, I'm going to have you do this and then give me a little feedback on it, because this will let me know where you're at. If y equals, hold on a second, which function? cosine of e to the x. See if you can do that. All right, so the outermost function here is cosine. And if I'm taking the derivative of cosine of something, I'm going to get negative sine of that same something. Then I have to tack on the derivative of everything else, but not the outermost function. And then the derivative of e to the x, though, is just e to the x. So I'm getting dy dx is negative e to the x sine of e to the x. All right. Give me a little feedback. Let me know if you were able to get that. If you weren't able to get that yet, that tells me something. If you were able to get that ahead of me, all right. So we're going to go now to the chain rule, what it means. So we introduced this chain rule with just some little tiny problems that we're kind of just getting used to how it would work out. The formal chain rule. dy dx is equal to dy du times du dx. That's the formal chain rule. And if I was in your shoes and I was looking at this, I would say, this doesn't look like anything that we just did. It doesn't look like anything like problem number 4. And how in the world can this be the chain rule when what we did was up here? And let me show you how the relationship of this could be. Let's do a different problem. Y equals 2x minus 1 to the 6th power. Now, the way we just learned it, dy dx 6 to times 2x minus 1 to the 5th times the derivative of what's left over, which would give us an extra 2, which is going to give you 12 2x minus 1 to the 5th. Now, there is the answer. Let me show you how I'm going to get that same answer by looking at it in this manner. We're going to create a new function. Let u equal the inner function. And u will always be everything else except the outermost function. U is equal to 2x minus 1. It excluded the outermost function, which was 6 to the 6th power. Now, if u is defined to be the inner function, then you can rewrite y without using x's at all. How would I rewrite y without using x's? I would just say y is u to the 6th power. Okay. Now Leibniz had this idea. He thought, because this is Leibniz notation, he thought that just like in a real fraction, you see how this du and this du would cancel out, and then dy and dx would just simplify like here. He thought, and since he used this notation, he thought this kind of thing should turn out to be true. And the du's would cancel out. And so, now look at what happens here. This equation is u and x's, and there's no y's. And you can find from this equation, you can find du dx, take the derivative of the output variable in terms of the input variable, and that's just going to be 2. From this equation right here, there's y and u. So you can find dy with respect to u. And if you did that, 6 u to the 5th would show up right here. So then, if Leibniz's idea was true, he would say to himself, all right, dy dx is kind of complicated because of one function within the other function. This should be the same as dy du times du dx, and the u can be whatever function we want it to be, whichever one is convenient to use. And it was convenient to make it be the inner function. And then he replaces dy du with 6 u to the 5th, replaces du dx with this 2, and he gets 12 u to the 5th. But then the answer can't be in terms of u, because u is just something that we created to help us do the problem. You have to go back and replace u with x. The original problem with y's and x's, we go back to y's and x's. This is 12, and then u is 2x minus 1 to the 6th. Notice the answer I get here totally agrees with the way that we first learned how to do it.
Shouldn't it be to the 5th?
Oh, thank you. I'm really good at that. Especially when I talk and I write at the same time. All right, now, when we do these problems, we don't do it this long way. We do it the way that I showed you, this shortcut way. It's quicker to do the chain rule this way. Just take the derivative of the outermost function and tag along the derivative of everything else. And then we get down to this. But when we conceptualize what the chain rule is, this is the idea that we're using. And it's a really simple idea that these du's should cancel out over here for whatever function that we make up in between those two. All right. So we can look at all of these problems this way if we wanted to. We could come back to this earlier one here. We know this derivative turned out to be negative e to the x sine e to the x. If we had done it with this notation, we would have done it like this. Let u equals the innermost e to the x. And then we could rewrite y without using x's. It would be just cosine of u. Now, this top equation, du dx, is, what's the derivative of e to the x? It's just e to the x. The bottom equation, dy du, what's the derivative of this with respect to u? The derivative of negative cosine of something is, or derivative of cosine something is negative sine of that thing. And so then, dy dx would be dy, this new intermediary u, times du dx. dy du is negative sine u, and then du dx is e to the x, and then this is negative sine, and now u is e to the x, times e to the x, and then if we replace it, putting this one first, we get exactly the same answer that we had before. So this is a conceptualization of the chain rule. Oops, I screwed up. Let me do this again. Print screen. Paste it, and let's come back over here. All right, now when we actually use the chain rule, though, we tend to use it in a different way. So we'll call this version 2 of the chain rule. And this is how we actually use it. And let me find this portion in my notes. Hang on just a second. Y equals f of g of x dy dx is we take the derivative of the outermost function. We leave the innermost function intact inside that. and then we chain along the derivative of the inner, like this. So this is how we actually see the rule in a way that we use it, where the other one is kind of a bit of why the rule works is because of that simple cancellation in those fractions. And let's do another more complex example where we take y equals sine squared of 3x minus 5. Okay, so let me send you to your groups, and I want you to identify 3 different: the innermost, the next innermost, and then the outermost functions. And I'm going to call on a group in a little bit. See if you can figure that out for this one. What's the innermost, next innermost, and then the outermost function? Okay, anybody need more time? All right, let me have group 3. What's the innermost function?
We said the innermost is 3x minus 5.
The next innermost?
Is sine of x.
Very good. And the outermost?
Is x squared.
That is correct. All right, now, if we see this as really 3 functions, now it would be much easier to see this if we didn't use this shortcut notation. There it looks like what we just said. There's the innermost, there's the next innermost, there's the outermost. It's harder to see it over here. But once we identify that, if we're going to do this using this schema for how to take the derivative, all we have to do is concentrate on the outermost function. The innermost, the g, can be more than one function, but the f cannot. The f has to be just one. So we put all our attention on the f, the outermost function. So we look at this and we think of the outermost function, which is x squared. This is y equals something squared. That's how we reduce this into something that we can use this rule for. So now we're going to take the derivative. So this is kind of a complex use of the chain rule, because it's a double chain rule, because it's 3 functions. Function within a function within another function. All we have to do is concentrate on the outermost function each time. So how do you take the derivative of something squared? Well, it's 2 times that something to the first power. And then you chain on the derivative of everything else. All right, with that structure, I'm going to give you a minute to get ahead of me. See if you can get this all the way down. All right, so the derivative of something squared is 2 times that thing to the first power. We could put a 1 there, but typically we leave that off. So that's what's in red is usually left off. And that's 2 times that to the first, and then that 1 could have also been placed there. And then times the derivative of everything else except the outermost function. So, common mistake is to put something like 3x minus 5. No, it's the sine of 3x minus 5, because everything else has got to be there. Alright, so then, this is the sine of 3x minus 5. Now here is another application of the chain rule, because you have a function within another function. We just focus on the outermost function. Think of this as the sine of something. The derivative of the sine of something is the cosine of that something, times the derivative of the inner one. Now the derivative of 3x minus 5 is 3. This 3 and this 2 are going to combine. It's going to be 6. And then sine, cosine. And that's it. We found our derivative. Now, give me a little feedback. Are you totally lost? Are you getting it? Feel like you could get it with a little more practice? Tell me where you're at. Okay. Now let's come back to here, and I'm going to copy this in. Okay. Now, what we're doing with the chain rule, if we look at it from a certain perspective, it can be a very intuitive thing that we're doing, although the manipulations become complex. Well, actually, so I have an explanation of why it can work, of why the chain rule works, but you know what, I think in this last, we got 7 more minutes, I'll save that explanation of why the chain rule works and why it's the way it is. Let's just do one more practicing how it works so that you're ready for the homework assignment. Okay. And let me look here, pick one of these that I want to alright. Let's look at this example. G of x is equal to x divided by e to the 3x. Alright. Now, you might think, hey, this is not a chain rule problem. Actually, it is. E to the 3x, that's a function within a function. And we're going to start to see why it was that that had that crazy rule, how that got to be its derivative. We're also going to see something else. What rule would I have to use here? Normally I would say this is the quotient rule. But now I don't have to view it as the quotient rule. I can call this e to the negative 3x, and I can call it the product rule. So I'm going to use the product rule. So I'm going to do g prime of x is first times the derivative of the second plus the second times the derivative of the first. To do this derivative, that's just 1. To do this derivative, I need a chain rule. Now, the derivative of e to the negative x, what's the innermost function? Negative 3x. What's the outermost function? E to the something. What's the derivative of e to the something? E to the something again. Now, we have to take the derivative of the innermost. But what's the derivative of e of negative 3x? It's just negative 3. So when we said before that the derivative of e to the kx is k times e to the kx, now we're seeing why that's true, because we had to tag along the derivative of the innermost function. So g prime of x is equal to, I'm going to have this negative 3, this thing, and this thing. I'm going to put the negative 3 first, the x next, and the e to the negative 3x last. So the more simple things up front, the more complicated things in the back. Plus e to the negative 3x. And that's my derivative right here. So note, y equals e to the kx. We had just memorized before that dy dx was k times e to the kx. But now we can say this is e to the something. The outermost function is e to some power. The derivative of e to the something is e to the something. And now we see why the k shows up right here. So the dy dx is k e to the kx. All right, we are out of time. The homework is 3.7. The chain rule. And any questions? Comments? All right.
Yeah, actually,
Yes.
my group just kind of was wondering if you could cover the not this last problem, but the one before where you use the chain rule twice, and just
Okay. And you want another example on that?
yeah, example, I guess, and some clarification on that would be helpful.
On the same problem or a similar one?
Just similar, like where you use the chain rule multiple times.
Or a similar one where you use the chain rule twice. Okay. Let me. So will officially end right now, and so, but I will spend a little more time here for those who have the time available, and this will be recorded, so if you have to run to something else, you could also look at this on the video. And let's do one where you do the chain rule twice. And of course, if you're totally comfortable with the other one, you can just stop right here. Alright, let's do y equals e to the tangent of 3x plus 4. And let's do the derivative. Alright, so Christian, I'm going to pick on you for a moment here. On this one, what do you think is the outermost function?
The outermost function, wouldn't that be e to the x?
Very good. So we just think of this as e to the something. So to take the derivative, we just keep our focus on the outermost function. What's the derivative of e to the something? It's e to the something. Because the derivative of e to the x is e to the x, so we follow that same pattern. Then you have to tack on the derivative of everything else. The only thing we took care of was e to the something. So all the rest goes here. So let's keep going. Now the derivative of tangent of 3x plus 4. The inner function is 3x plus 4. The outer function is tangent. So we think of this as tangent of something. And the derivative of tangent of something is what? Derivative of tangent x is secant squared. That's something. We have to tack on the derivative of the inner function of everything else. We only took care of the tangent, so everything else stays there. And this, its derivative is 3. So then y prime is going to be 3 secant squared 3x plus 4 e to the tangent 3x plus 4. That would be it. Right there. Any questions? All right, well, thanks for bringing that up and for representing your group there, Christian.
And thank you for the extra explanation and example. Have a nice day. I think that's it from my group.
Okay, great.
So.
All right, I'll see you all tomorrow.